In this section, we're going to cover probably the largest paradigm change that will be required for most people to truly master Swift. That is, protocol-oriented programming. We'll start by covering protocol extensions and go on to demonstrate how their application leads us to begin working in a very type-free style, whereby we stop thinking about what values are entirely, but only on what they can do. By understanding this, you discover how Swift's standard library collection protocols such as sequence and collection are able to share their behavior without traditional inheritance. Hopefully this section will put you on the path to making the most of this great programming paradigm. We begin our journey in protocol-oriented programming by learning about protocol extensions, the key feature which enables this shift of programming style. Let's start by outlining the basic problem that protocol extensions seeks to solve. Fundamentally, this is a question of allowing types to inherit behavior from other types. There are many other solutions to this problem in other languages. The solution most programmers will be aware of is object-oriented class hierarchies. Let's start with a classic example of single inheritance. Here we have a hierarchy of vehicles. At the top, we start with an abstract base class, vehicle. It merely defines the interface that says all vehicles can drive. Then, as we move down the hierarchy, we specialize into concrete types, which add more and more characteristics. The main benefit is that we can potentially reuse a lot of code, and at first glimpse this seems elegant and understandable. One obvious limitation of single inheritance is that we can only inherit from a single parent. So why not support multiple inheritance? Well, unfortunately, this brings its own problems. Multiple inheritance seems like a nice system. In theory, we have the ability to mix in the methods of various classes. This means we can have an abstract base class, two subclasses A and B, and a subclass C, which mixes the functionality of both subclass A and subclass B. However, there's a classic problem with multiple inheritance known as the diamond problem. If we have a method called doSomething, which is implemented in both A and B, which version should subclass C use? This is the basic diamond problem, which leads to ambiguity. Let's summarize the problems we have in total with single and multiple inheritance. There are many points here. We've seen that single and multiple inheritance have issues, but more than that, the attempt to model using a hierarchy often becomes large and complex. In particular, hierarchies become rigid, making refactoring very slow and difficult. We also see a gravitational pull of code towards the base class, and many hacks to work around the quirks of the somewhat artificial hierarchy we build up. So before we go on to look at protocol extensions, let's consider what features we really want from a system of behavior inheritance. We can summarize these as above. We'd like to be able to adopt behaviors from other types, but we don't want the associated lock-in that object-oriented hierarchies often force us into. We saw in my previous course, Exploring Swift, that many features of the language encourage us not to use inheritance at all. Prefer structs, use the final keyword whenever possible, as well as needing to use the open keyword explicitly to permit subclassing of our classes. We want to reuse code really, but we want to avoid these issues and any associated hacks. So, protocol extensions are a feature that tries to provide all of this for us. Let's look at a definition of what protocol extensions are. Apple's Swift programming guide provides the following definition for protocol extensions. This allows you to define behavior on protocols themselves, rather than in each type's individual conformance or in a global function. So this is a very simple definition. In fact, there's nothing difficult to understand in how to implement and use protocol extensions. The challenge is really adopting the mindset that makes them powerful. Let's go straight to a simple example. In my course, Swift, the Core Concepts, we did a lot of work with simple types and protocols with names. First names, last names, full names, etc. Here's another similar protocol. We have a requirement that adopting types provide a first name, last name, and also a full name. We explain protocols as describing what a type can do. In this case, every type must be able to provide a first name, a last name, and a full name. Notice that the requirements of the full name property are actually based on the capabilities of the protocol itself. Therefore, it's a waste to force adopting types to define this method. All the capabilities we need are already in the protocol. This is where we can use a protocol extension to provide a default implementation. The syntax is simple. We use the usual extension keyword, except we don't extend a normal type such as a struct, class, or enum. Instead, we extend the protocol itself and provide an implementation for full name, first name followed by last name in an interpolated string. This provides a default implementation based on the capabilities of the protocol or a protocol it might inherit from. Types that adopt name protocol now do not need to provide this implementation, unless they want to override it. Now let's consider implementing this on some types. Let's start with an example of a Western style name. In this case, our requirements for the full name match the protocol extension, writing first name first and last name second. But how about when we want to adopt this on a type with different requirements? In this Japanese name type, we want to print the last name first and the first name second. How can we do this? We can't use the default implementation. Well, no problem. We simply override the default implementation and provide our own, as I've done here, with the full name property on the Japanese name struct. Perhaps you can see that this seems very similar to multiple inheritance. Don't protocol extensions suffer from the diamond problem as well? Let's look at this hierarchy. We have two protocols, A and B. Both require a method called doSomething, and both provide default implementations for doSomething in protocol extensions. What now happens when we try to adopt both A and B on a struct? We can't. The compiler will complain that foo does not conform to one of the two protocols. This is actually not a very helpful error message. What it actually means is that we can only conform to one of the two protocols because of the protocol extension method conflict. Can we resolve this conflict? Yes, we can. Overriding the default implementations with our own in the struct foo. Now we have no error. We've explicitly implemented the method ourselves and thus resolved the conflict. This is Swift's solution to this problem. There's no ambiguity now. We must be explicit. Also, because there's no actual inheritance, there is no way to call the default implementations from either protocol A or B. This is an important difference. They are default implementations. If we don't want to use them, or we can't use them, we simply provide our own implementation. Let's summarize the benefits of the protocol-oriented approach. Protocols can be formed into hierarchies, but without default implementations, they are just interfaces. When we use protocol extensions, we can inherit these default implementations, but we always have the ability to override them. This prevents us from calling back to the default implementations, which also avoids the kinds of hacks that this can lead to in traditional inheritance. We must resolve method conflicts explicitly, but this in fact rarely happens in practice, since protocols tend towards the small and focused. Protocol-oriented programming also brings most of the power of inheritance to types that don't support traditional inheritance, such as structs and enums. This strengthens the case to prefer value types with protocol extensions over classes with single inheritance. Overall, it's hard to make the strongest case for protocol-oriented programming until you've really spent some time working with it in your code. We'll continue in this section, however, to present some examples that should communicate to you the power of protocol-oriented programming.